Hello everyone, my name is Ludmila and I've done my research project on neural networks, more specifically how functions and derivatives are used to power the network's algorithm. So what is it? A neural network is essentially just a model that mimics the way that the human brain processes information. It recognizes patterns and creates predictions based on information that was given. The network is a web made up of nodes which act similarly as a neuron in the human brain does. It works by sorting through the information it is given at the start in the form of inputs. It then goes through layers that are hidden which process every possible prediction, then the network will produce its outputs and give you its final answer. The concept was originated from neurophysicist Warren McCulloch and mathematician Walter Pitts in 1943 while constructing a model of neural pathways. They created this model using electrical circuits, and once computers became more advanced towards the 50s and 60s, more viable models were getting built. With more research and funding, the basic neural network that we have now was developed using Woodrow-Hoff's idea of recognizing patterns and the use of weights like 0 and 1 to look through the data. The idea in this concept was that if the human brain is able to resolve issues, so should a computer model of it. Today, neural networks have many purposes, from using Face ID on your phone, making self-driving cars work, and detecting diseases in medical images. So what is the math behind making the computer model of the human brain work? Well, it is done so with inputs, hidden layers, weights, biases, and outputs. For example, when scanning an X-ray image, a neural network may be used to find a tumor. The pixels in the X-ray image would get assigned a numerical value and serve as the input layer of neurons. The input neurons would then move through a channel where they are multiplied by weights and the sum is added to a bias. Weights are just small numbers that are randomly chosen to help the network begin identifying a pattern, and biases are also a number that tells the weight function where it needs to be in order for the network to yield its output. This is the algorithm. Each hidden layer will focus on different specific factors that make up the image as a whole. For example, the resolution of the image, the contrast, the brightness, etc. The neurons will continue to form hidden layers with weights and biases that give the most accurate data until a viable output is produced. The network of neurons works with this basic formula. W is assigned to the weights value and B is assigned to the bias. X will be all other variables that are produced. In this case, X will be the numbered pixels. These pixels are each multiplied by a set of weights and then as a sum added to its bias. In the following layers of the network, X becomes the inputs from the previous layer. W is the weight values that found some contribution from the previous inputs, and B is the bias value that allows for more flexibility in the formula by adjusting the output to fit more data in the network. If there were no bias value and the network solely relied on its weights, the output would always be 0. The bias being added to the total weighted sum of inputs is crucial for the algorithm to pick up on patterns in the pixels. To help unpack this formula, Jeremy Jordan wrote an article which I found useful for my research called Neural Networks Representation, which shows this model of the formula in vector and matrix form. Here he has colored each neural pathway to help visualize how the network formula works. The inputs X each have a connecting line to an output. This line really just represents the value for weights that is labeled with the variable W for each neuron in the matrix. It then gets multiplied by each input value, which is shown in the vector with the variable of X. Then that sum is added to its assigned bias value for the neuron, which is shown here in the vector with variable B. This formula's purpose is to allow the algorithm of the network to check which of the weights and biases yield the most accurate outputs and start recognizing a pattern in the image. To minimize error, at this point the network will put its output values into a loss equation like so. The value of Y is the final output that will get passed to an activation function with the objective of fitting the data thus far into a range from 0 to 1. The sigmoid function is most common for this process as its domain is infinite and fits all real numbers while its range is from 0 to 1. As Marine Sahid refers to it in his article A Gentle Introduction to Sigmoid Function, it is the squashing function, because if the input is either a very large negative or positive number, the output is always between 0 and 1. Same goes for any number between negative to positive infinity. Basically, the data that yields very large positive numbers will be closer to 1 on this range, and large negative numbers will land closer to 0. Here we see that the inputs labeled with the variable X are passed through channels of weights that are labeled with variable W to output a weighted sum that is used to squish the data between 0 and 1. To better understand why this function is so important to neural networks, here's a list of a few of its components that Sahid created. The green line on the graph displays the sigmoid function itself, and the pink line displays the derivative of the function, which could be used later on for the network to check for error in its system through backpropagation. The process of backpropagation in neural networks is just finding the derivative of its activation function to help minimize error when predicting the network's output. Here I found a model on Enjoy Algorithms article, Calculus Chain Rule for Neural Networks and Deep Learning, of how the chain rule is applied to derive the sigmoid function. Basically, the derivative helps fix the value of the weights and biases until the predicted output matches up with the desired output. The value which the sigmoid function provides is really just a measure of how positive the number is based on how close it lands to 1. Now let's say that the closer the neurons yield to the number 1, the more likely it is picking up in the pixels that there is a tumor in the X-ray image. So the neural network is just examining each pixel layer by layer for a specific area that will produce many outputs that are very close to the number 1. Once the network has found a pattern that could confidently diagnose a tumor in an X-ray, it will predict where it is on the image with its final outputs. This could look like highlighting the pixels that had weights and biases which showed to land closer to 1 on the activation function. So to conclude, neural networks use calculus in many different ways. I only managed to scratch the surface here with the formula they followed, the activation function and its derivative. But really there is so much more to unpack in neural networks relating calculus concepts. Neural networks are getting used more and more every day with AI and deep learning. It is really at the core of every application now, and it still has so much more potential, especially in the medical field and biology as a whole. If any of you are interested, I have added the articles mentioned in this video to the description. Thank you.